I view it as a challenge, which I'll explain in a moment. But just to help me with this challenge, I understand there is some meaning of assignment here, which I don't know exactly what the practical means of it. Anyway, the assignment which I would like to give you is up to tomorrow night. Please send me an email or come to my office with 1 up to 3 objections or things which bothers you about many word interpretation. So don't put 10 pages, and then, but I'm pretty sure that at least one objection everyone should have.
So that office is room 450. Room 450 at PI. He'll be here today and tomorrow. And probably at IQC on Thursday if you want to track him down.
And my challenge is the following. I looked in Wikipedia recently on many word interpretation, and they have this piece from a course 5 years ago here. I understand there will be, probably will be again a survey about different interpretations. And what I found that many words got a sign -7. First I saw that maybe kind of minus plus was kind of mistaken. Because from my point of view, if you multiply everything by -1, then it will be a correct picture. So let's see how much I will be able to do towards this. But first, since it's a talk about many word interpretation, I really want to do it at least in 3 different words. And in Tel Aviv, where my students set up a quantum optical device, which allows you to split words from 2 to 6. And I want to split it just to 3, so I arrange it. Let's see if it will work. Okay. So all what you have to do, if you want different options in your life, and you cannot decide, go to this site, to my home page, and then there is this quantum word splitter, and put different options. You have to have a strong will. You put here, now it's very simple, because what I will do is just to put here left. And here I will put, let's center. And here I will put right. And you have to force me that after I will make, now I have to make a splitting. When I push this button, there will be some single photon experiment. In fact, it's run all the time. It will take some. What I have is just a very simple laser, beam splitter, and single photon detector. And I test in which time exactly it happened. And this is a quantum effect. So I'm pretty sure that when I push this button, there will be 3 words from now. There will be one which will tell that you are in a left word, center word, and right word. 3 different words. You have to ensure that I will follow the instruction. Center, I will not move and start my lecture from here. Left, let's decide left here, your left, so I will go there. And right, I will go there. And I will continue from then. And from what I know, that it's not really just Lev Weidman, one Lev Weidman giving one talk here. It will be 3 talks, and it will be somewhat different because, you know, if you start a few meters apart, maybe they will be not exactly the same. So let's do it. Center word. Here I'm lucky, I don't have to work hard, I don't have to move, but I'm sure that there are 2 others. So let's continue. Also about questions, you are welcome to stop me if something's not clear. any moment. And you are welcome to use this device for more important reasons, not just being here and there. What I will try to persuade you that all is psi. All what's around, all nature, everything is just quantum wave function. And I think it's a real challenge in this course too, because if I looked on the program, you have 1 week on probability, another week on different probability theory. Just last week, a superior statement about the objective characteristic of our quantum world, of the things in it, would contain no psi at all. So I think I come to an audience which kind of was taught to believe in something completely different. So I think the reason, maybe some of the reason, it's what is my starting point, what I want to do with this theory. And I have a hope that today's physics explain all what we see. Moreover, I want to believe that today's physics explains all. I'll never be able to know this, because maybe there are things which we didn't experience, didn't come here, far away, new laws, we don't have these energies. But I might expect that basic physics, we know, explain everything. If I don't see any paradoxes, real paradoxes, something which I cannot explain, I have to believe that this is the situation. So this is my purpose, and I think this is what physics is about, trying to find such a picture. Now, when I have this purpose, and I look what we have in physics, we have wave function and quantum mechanics, and I don't think we have any other good candidate. So if it's not psi, I don't think today we have an attractive candidate. So this is why I want to believe that psi is all. If I look on the beginning of quantum mechanics, Bohr will tell us that the quantum mechanical formalism does not provide physicists with a pictorial representation of representation. The psi function does not, as Schrödinger had hoped, represent a new kind of reality. Instead, as Born suggested, the square of the absolute value of the psi function expresses probability amplitude for the outcome of a measurement. Bohr and today's majority of physicists gave up the hope. And it seems that here, which from as far as I know, the only place in the world which really is the center of foundations, I think this should be the center of the hope, and it seems the direction, even here, look different. I think we should not give up the hope. If I look at this course, of course, the main goal of the science is to predict and control phenomena. I don't see it this way. But I think there is an opening in this course, and this is maybe the reason they still decided to bring me here. But we also want to understand how nature works. For me, the basic problem is the second one. We'll understand how nature works. We can help engineers to control things. But I think the main thing which I'm trying to do is trying to understand how the nature works. And I believe that except psi, we don't have any other candidate. All this psi. I have to specify a little more what do I mean by this. And first, what's all? Essentially, it's related to many word interpretation, because when it started, cosmologists took many word interpretation. And the reason was that if you use orthodox interpretation, textbook interpretation, you need an observer. And they said, if I have the whole universe, there is no observer. So they had to look in the whole universe. And I think many proponents of many word interpretation, at least in early days before the quantum computer, were just cosmologists. From my point of view, it's not necessarily everybody who would push in this direction, I'm happy. But I don't think this is not my reason for this. All for me, it might be a closed system. If I can describe a closed system to understand exactly what's going inside, then if I'll bring an observer inside, and I can understand how the observer understands what he sees inside, this is good enough for me. And I really don't want that this system will be really, really close, because I do want to put some external disturbances and to see how the guy reacts. It's very difficult if we assume that everything is given. Then we can say, oh, a very special condition, which when we make this Stern-Gerlach experiment for EPR Bell type setups, then somebody fixed this direction. I want a theory that I can fix it freely. Outside the box, there is a free will. Inside the box, there is a deterministic theory, but I have to understand how things work. If I understand exactly what's going, how he reacts on internal or external things, this will be good enough for me. This is what I'm looking for. Now, what is, yes?
So I'm a little confused by your language here. When you say all is a closed system, which I guess is basically just constrained to what your man in the box observes, are you saying that includes all things that he might observe in the future? Like is this at a fixed point in space-time? Whatever he's aware of at a fixed point in space-time is your all, or is it like something in the future or something in the past as well? Or?
I have to understand his behavior, and looking on a single slice of time is not enough. I want to see its evolution. I do something to him, he reacts, I understand why he reacts and what's going on. I don't have to look from minus infinity to plus infinity. I understand it for a long, finite time. Good enough.
Okay.
Then,
so it seems in that view, it seems like if you're using that language, you've already committed yourself to the idea of a single future, which seemed, and you know, I read your Stanford Encyclopedia of Philosophy article yesterday, and it seems like you're already contradicting where you want to go, right? Like if we have to say, to understand what is all for this guy, we need to sort of take some span of time, right? Which will encompass his future. Then it seems like we need to say that this guy's going to have a unique future to talk about.
did they say unique future?
Well, he didn't say unique.
I did make, I had the first slide, and the first slide got some impression, feeling that there are parallel worlds. There's another guy walking here, maybe now across me. I probably had to do it also in this picture too, but, you know.
Right.
Of course, if the guy inside will make Stern-Gerlach experiment twice, X and Y, he will split. Mm-hmm. But I'm outside, and I love myself that I have technology to see whatever he does.
Oh, okay. That's interesting.
Yes.
So then, is your all thing of disjoint closed systems? If it's multiple, if you're not just constricting yourself to one future, unique future, and you have this branching you're talking about, do you have disjoint systems then? Closed systems that consist of your all?
I will soon say, and soon will tell us. And in fact, I already told this. The name was many word interpretation, but then I saw all this psi. So it's one psi. I will explain later why I think the naming many word interpretation is a proper name. But there is a one universe, one physical universe. So I'm outside, it's just one, and look what's going on inside. Inside there will be many different stories for the guy if he would make quantum measurements. But it will be just one wave function. which will include all multiple stories for him, which people call walls. Yes?
So you say all is a closed system which might include an observer and then which we are observing. Well, then if we're outside the system, then it's not all. Right?
So I will try to make it. There are kind of philosophical paradoxes when you try to explain yourself. And some people say that this prevents for theory of everything. Maybe I'm not enough a philosopher to value this. So for me, if I have a closed room with a few people and experimentalists, and I can observe exactly what's going on, and I have a complete theory, complete understanding what's going on, then I can extrapolate to say, oh, I'm like him. So of course, I will realize for these guys that when I'm outside, I see all his words, all his different copies. When I myself, I will realize I don't see other copies, but if I understand what's going on for him, oh, it's something similar for me. I'm one like him. So I want to believe that the whole universe is always described by psi. If I can understand how this psi describes this closed room with a few guys and a few experimental devices, then, and I have a good theory of it, I think this is enough to make this extrapolation. So this was the point of all this all. Is it clear? Okay. So what is psi? I can recommend this new book. There are a few entries which I believe are correct there. There is no sharp answer. Theoretical physicists are very flexible in adapting their tools, and no axiomatization can keep up with them. But it is fair to say that there are two core ideas of quantum field theory. First, the basic dynamical degrees of freedom are operator function of space and time, quantum fields. Second, the interaction of these fields are local in space and time. So this is what Wilczek wrote about what are quantum fields. In fact, I was trying to find on the internet wave function of the universe. I was pretty sure that I will find a lot, and I didn't. There are all kinds of theories, but people who are working in high energy physics, it looks like they very fast became operationalists. If they can understand what's going on with their particles and accelerators, so they don't try to discuss the whole universe. There are a few theories, and when you talk to people, strings and whatever, they say, oh, there is this formalism. Then there is a wave functional of the universe. It has all kind of pretty complicated properties, but forget about it because it's very inconvenient for calculation. So, in some place, there is hope. And if there will be a wave function, and clearly it's a wave function of fields, not particles. We know quantum mechanics of particles is incorrect. And I think there is no enough research in this direction. I'm not capable really to do much in this field. I hope to at least to make other people to work on. Anyway, for this course, I don't think it's relevant. We are talking about interpretations of foundations of quantum mechanics. And the paradoxes and problems sits in a level when we don't do supernova or nuclear explosions. So almost everything we see here, Schrödinger equation, even non-relativistic Schrödinger equation, is good enough. And it's still, when we make this measurement and there are collapses or no collapses, as I would try to say, it's still here without this special thing, complicated formalism. So psi of R, of particles, is good enough. I can limit myself to psi of R and discuss kind of normal physics. I will not be able to discuss early universe. It's important. I hope that it will not bring any kind of new thing. It's not absolutely clear, but at least if we don't have paradoxes in describing phenomena in this scale, we can hope that we can do relativistic field theory with and all cosmology, everything from early universe till and gravity. I don't touch gravity. I take here space as granted. Clearly, there are some problems. I don't feel that they will make a revolution. The language has to be changed somewhat. So, in this talk, space is taken for granted. We have some wave function in this space, psi of r. So, this is kind of a framework. What I'm trying to say is that there is a good, not contradictory description of everything we see with a wave function. The first point which I want to make is that I really don't want collapse in this wave function. I think it contradicts everything we know in physics. So, the first point, I believe there is no collapse. And I will say why I don't believe in collapse. In fact, two things, randomness and action at a distance. So, let's see. If I accept that everything is just psi, and I accept there is a collapse, then automatically, immediately, we have randomness. I consider a particle being here and here, and I make a measurement trying to find it here, projection on A. Now, it may come out 1, it may come out 0. And quantum mechanics, by definition, tell us that it's a random event. This is what's quantum mechanics. If we have only wave function, only we don't have hidden variables or anything like this, then by definition, this is random event. There is nothing which will tell us. I think very important, until in classical mechanics, we didn't have randomness at all, and now we have randomness. Now, positive, negative, something very, but from my point of view, I would like to try to avoid it in the end. Quantum mechanics give it with a collapse, give it immediately. Now, it also gives us action at a distance. We can rewrite this state, A plus B, just single wave, single photon, whatever, boson, whatever you want. With fermion, there are some difficulties. Everything we can rewrite in this way. And this is really an EPR state. We can look on it like up-down. Now, for photon, in principle, for any boson, we can clearly measure 0, 1, like Z basis. But we can also measure if it's 0 plus 1 or 0 minus 1. If you're not aware, Lucian Hardy from here has a paper, which I didn't like one's language, but I think essentially it's a very important paper and very important message, non-locality of a single photon. If you have a single photon in such a superposition, you can have a Bell experiment. You can measure essentially, and you can break Bell inequality. This is really standard Bell, like two-spin system or a single photon. It's the same story. So in this language, I can write the complete description, the complete quantum description of my photon here. It's just if it's present here or not present. And since it's entangled with other things, we will get this in what's called improper mixture. This is a density matrix. And we don't have any other. The complete description of this photon here is this density matrix. Now, if I'm going to do a measurement, then I will find some outcome. I'll find some outcome. I can find that it's here or not here. If I'll find that if I'll find photon here, it's not here anymore. So from now on, the description changed. It was density matrix half and half. Now it's definitely not there. If I find other outcome, it will be different one, but still not this. So clearly, collapse makes changes. Now, if we don't do any measurement, of course, no change. It was this density matrix, remains this density matrix. So it's collapse who made this action at a distance. Now, okay. If I make a measurement, if I make a measurement here, and I don't believe in collapse, I consider also a measuring device as a quantum system. What will happen? From this state, I will move to this state. And what is the density matrix here of B was this. But the density matrix here is the same. It's not important if presence or not presence of a particle here was correlated to presence or not presence of a particle here. Now it's correlated also to my measuring if it is present or not. But from quantum mechanical point, the density matrix here didn't change. So my act of measurement, if there is no collapse, will do nothing whatsoever. We still will remain with the same density matrix. So it is collapse who caused action at a distance. Without a collapse, the act of measurement will not cause action at a distance. No change if there is no collapse. Now, this was just an idea that we have only quantum mechanics and we have nothing else. And in fact, this would kind of say that maybe you can get different ideas about maybe something was wrong with quantum mechanics. I think Bell told us that it's just not quantum mechanics. Yes?
So you say that this is action at a distance, but I think it was last week that Chris Brooks was arguing that you see the same effect in classical Bayesian update, and that there's no actual action happening there. It's merely a change in knowledge. Do you have a counterpoint to that?
Okay. I think it's... Let me finish action at a distance in even a not justice psi, then I'll try to persuade you that this is not so. Okay, what Bell told us that if we want to find something behind quantum mechanics, to say that maybe things are not random, maybe we just don't know, they're fixed by something else, quantum mechanics is incomplete. You can say it maybe before this was a hope of Einstein. He didn't believe in randomness. So he hoped that quantum mechanics is incomplete and we sometimes will complete it. Bell showed that it's impossible. So since this photon in two places, it's like a PR case, it's impossible that there is a hidden variable which will tell us what will be the outcome. At least for one outcome, but then we can go for both. So when we make a measurement here, it has to be random because it was not known before. So now let's be very clear, what does it mean random? Bell told us there is no theory, no way whatsoever that before the measurement, the outcome is known. So there is a randomness, in fact, both here and here. That if you're going to make a measurement, there is a special, the complete description. So if you can try to talk about this kind of language, there is something very special here. There is uncertainty here. This area described by uncertainty. The outcome of a measurement which I'm going to do is unknown. This is the state of affair. And this is something which I think it has some operational meaning in a sense. That if I have this kind of photon, and even I'm far away from there, I'm ready to put bets on this outcome, and I know that I should put bets 50-50. If this part, I know the situation, I have this superposition, and this part is guarded. I look that it's in a box and nobody touches it. In this situation, I'm ready to put bets on an outcome there, 50-50. So the reality of this place is my readiness to put bets. And my readiness to put bets, I'm ready to put 50-50 without problem. Now, if I make a measurement here, and it has single outcome, I don't have to talk about even collapse or not collapse. I make a measurement here, I get an outcome. If I get an outcome, sorry. We just didn't finish randomness, repeat randomness, and I'll come back to action at the distances. I will try to, let's come back. The claim is that even if I don't accept that there is a wave function and collapse, just accept that there is this outcome of a single measurement. This tells us that there must be a randomness because this was not known before. If you not played a lot with Bell inequalities, I think GHZ is the best thing. GHZ tells you cannot have given outcomes because it comes to a contradiction. And quantum mechanics tell us that GHZ is correct. Therefore, this kind of situation, there is no outcome. It cannot be known in advance what will happen. Therefore, there is randomness. No measurement. Now we go to action at a distance. The same thing I can say about this one. It's still completely random. This is why I'm ready to put these bets half and half. It couldn't be defined before. Now I perform a measurement. When I perform a measurement, something changed there. And it's absolutely obvious what happened when I perform a measurement, but maybe somebody else near me make this measurement. In the moment he made this measurement, I will not be ready to bet with him on the outcome of this other measurement. Now, before I said, look, there is a real uncertainty here. He made the measurement. Immediately, I'm not ready to I'm not ready to make bets about this place. Clearly, something changed. A real thing changed. Operational meanings. Whatever you want to describe it, quantum mechanics, or if you had this, many talks have all kinds of probability theories, probability, whatever you describe this. In fact, what you described before, the only possible description was this density matrix. Because you know it's really, there is no, it's impossible to know in advance what will be the outcome. And it's not anymore after the measurement. So he can say information, whatever. And he doesn't want to talk about reality. If I want to talk about reality of this thing, Bell told me that it cannot be reality about what will be the outcome. The complete reality in this description. Since we know that quantum mechanics is correct, we have to, just observation of quantum mechanics tell us that independent of what is finally the theory, just that any theory correspond to outcomes of statistics of quantum mechanics, this has to be the case. Immediately after the measurement, it's different. I'm not ready to make a bet because he knows the outcome. Of course, he can win against me. Whatever will happen, this will happen or this will happen, there is a change. There may be this density matrix or another one. It's not this one. Now, maybe something like usually, and it's really important, when I perform a measurement here, I can get this outcome or this outcome. Now, it's random. Therefore, also there is kind of random event here. This outcome or this outcome. It looks like what people usually call a proper mixture. There is a chance for this, and there is a chance for this. First, I don't think it's relevant here, because when you make an experiment, you get one outcome. It's only maybe in my many words I can look on this kind of thing. But another thing which I want to say here, proper mixture. There is a meaning of proper mixture. I never found it. Proper mixture, I think even in this course, people consider proper mixture, improper mixture. There is no, I don't see any theory with a proper mixture. I know there is one theory which is classical physics, classical mechanics. Everything has exact position. We might not know this, might be ignorant. However, nature knows all the time. So proper mixture may be kind of technical term, cannot be foundational term in classical mechanics. We have another theory, which is quantum mechanics, which tells us what it is. It's improper mixture. Now, there are all kind of, I understand, games playing to all kind of theories which introduce this concept, but maybe there is a randomness, but there is no theory. We have a well-developed classical mechanics explaining a lot of things. Finally, fortunately, unfortunately, we know it's incorrect because experiments tell us this is does not work this way. Then there is another developed theory, quantum mechanics. But there is no theory of kind of with randomness inside which explain everything, anything. There are kind of additions, like people add randomness in all kind of collapse theories, Nelson, all kind of, but I understand that Tubulka said Nelson didn't failed. And of course people who work on, he also has some kind of random flashes, and at least all kind of, but this is, anyway, it's not a theory, it's kind of additional element. There is no theory with a proper mixture. So, if I kind of believe that there is a wave function and explain everything, and I have, for me, very convincing argument, don't believe in collapse because collapse has this randomness, which no other physics have randomness. There is no randomness in physics. There is no random phenomena. And there is no action at a distance. And I can rely on Wilczek, who said everything looks like it should be local. Then the whole story is just a single universe with this wave function of all particles. Now, the question, why did they come to this point so fast? It's like using half of the first lecture. Why do I need to continue? Okay, the nature is described by the big universal wave function. It doesn't have collapse because collapse is ugly, it's non-physical, and we don't have any kind of good explanation for it. Why do we need to work more? A century ago, people kind of thinking that the hope which I had was achieved. The work, I don't know, it's still the history, it's hard to understand, hard to know. I'm not really a historian of science. But I understand that a large amount of physicists, of people believed that the physics is finished. That we had these classical Newtonian laws that in large explained everything. People said that there is a Laplacian determinism, mechanics. Now, and according to this, everything was described by particles. Cat was many molecules, atoms, they're all particles. All these particles have trajectories. And they all move according to Newton's law in some electromagnetic interaction, which then knew very well. And so people believe that they finished physics. And I'm not aware that people were talking about all kinds of interpretations. And the reason is because the correspondence between the picture of all this particle moving to our experience, to the things we see outside, is trivial. We just, all these particles, we look on all these particles, they look like what we see around. Tables, cats, chairs. This correspondence is really trivial. However, if I say that we have this wave function, the big wave function which describes everything, the correspondence to what I see is not trivial at all. In fact, at most it looks like what I can hope, it's for consistency. That my experience is consistent with this my assumption that everything is just a wave function. Moreover, this sign is not a good sign here because maybe this is okay. This big wave function will tell us my particular experience. But clearly, this experiment will not tell me the whole wave function. What we know that we need many experiences. Then there is a hope also for error in another direction, for correspondence. So the correspondence is between this one big wave function and many experiences. So this is really the many-word interpretation, trying to find how I can put together, first, the mathematical physical theory. Everything is just a big wave function. And what I see around, what everybody see around, people make experimental data, everything people know. So this is the task of the many-word interpretation. I have to make correspondence between many experiences. This I have to admit from the beginning. I would hope, of course, I would like to have one experience, one word, much nicer. I don't want many words because I want many words. Like some philosopher says, it's not so bad idea, like Lewis. But I want a good physical theory. I want to believe that the current physical theory roughly explains what we see. Current physical theory doesn't have randomness, doesn't have action at a distance. So, therefore, I'm forced to believe that there are other words. And I'm forced to believe, and the only way to explain it, that there are many experiences. Now, these many experiences, I will call many words. From my point of view, these three words, when I'm walking here, I'm pretty sure that the other two labs are not exactly in the same place. Maybe they will ask questions in some different moments. They're probably in a different slide. They will finish this lecture in different times. They may be late to an airplane back. There will be very big difference. So I think they will have different experiences. This is what I will call the different words. This is one word, and there are different ones. I know, I'm sure, at least that there are three. I made the experiment. I believe in quantum mechanics. I believe that there are at least three words now. Now, if I want to make this mapping, I have this experience. One experience, what I called one word. And this one word has some mathematical counterpart. I have this big wave function, the universal wave function. I can decompose it to a superposition of different branches, the different parts. And each part corresponds to an experience. Experience, what I will call a word. Now, one way to define the word, just by what kind of experience. Maybe another word, in fact, there is ontology. The whole ontology is just a wave function. Tell me, if I specify exactly the branch, it's also telling me what is the word. In some theories, like classical theory, you just put an ontology and you understand immediately what the word is, what the experience. Here, I think, again, they all goes together, but I think the way, kind of more fruitful way to find correspondence and from this definition, and then trying to understand what is this one corresponding to the particular word. Yes?
You also have equivalence between experience, history, and record? Or are those distinct?
No.
No.
The experience is particular, okay, everything, one can go far away, then it will be not very interesting to look on 1,000 years for myself. But experience doesn't have much meaning for a particular time. What's important, I have to look on a period of time. I can have some physics that if I know exactly what will happen now, then during some time it will evolve, correspond to experience. And usually I will not every time will talk, oh, there is a period of time. But clearly, in zero time, I don't have experience. So I need some reasonable history. Now, it's a good idea if I'll call this experience I, at least in this picture. This is really in particular, splitting in particular time. there is this difficulty, then we have splittings. Not very clear how often, but we do have them. So let's say, and we have the splittings. And what is 1 psi I? The simplest thing, if you just look on the period of time, no splitting. But if I want to call the whole word, in fact, what's important, it's this one. There are some splitting, but there is a one. I will start it from some particular experience. Every time, so it will be something of this kind. Yes?
Is it always referring to some observer then?
Let's postpone this, because I will discuss this. Okay. Because, in fact, what I'm going to do now, okay. So I have to, one of the main thing in many word interpretation is to explain what the word is. Again, the whole picture, one can say, wave function of the universe, no collapse, period. But then I have the job. I have to make correspondence between this statement and my experience. And for this, I need all kinds of concepts. And the word is this kind of a concept, is a concept for us. From a mathematical point of view, it all sits here. No more physics. This is just the task, correspondence between physics and experience. For this, I need the concept of word. I think maybe it's somewhat oversimplification, but Everett proposal, also his paper has a relative state formulation of quantum mechanics. What he considered is really a word for a particular observer. For words, he takes a particular observer and he says, this observer, like me, here, walked here and here and here. There are 3 words at least for me. I decided. Then you come kind of together because in interaction with me, there was a split. But this is the splitting when I want to define words. They were defined for particular observer. So in this, we have big universal wave function which separated to this kind of branches. In each branch, there is a product state of an observer in a particular state of mind which he understands, and all the rest. And this is a relative state. Again, psi is not the whole, it's a particular branch. And each branch, it's only of this kind. Now, I think this is consistent. You can work with this. It's a nice theory. I prefer a somewhat different approach. It's not in contradiction. Again, it's just what you would define as a word to make picture plausible, understandable. The task is to make correspondence between experience and the universal wave function. You can define whatever concept you want. I think historically, this was what defined by Everett. I prefer something a little different. A definition of a word on the left side, on the part of the experience. For me, a word is a totality of macroscopic objects, stars, cities, peoples, grains of sand, etc., in a definite, classically described states. All macroscopic objects are not in a superposition. I don't, if for Everett, if it was a supernova explosion far away, and no signal come here, for him there is a superposition of explosion and not explosion. In the world in which supernova, like Schrödinger cat, Schrödinger supernova, or if there is an isolated device with Schrödinger cat, for Everett, in fact, okay, the cat is in a superposition. I say it's okay, but I prefer a different language. In my language, there are no cats in a superposition. If there was a Schrödinger cat experiment, we have now 2 words, one dead and one alive cat. All objects, all macroscopic objects, have to be in particular state. Electrons, photons, neutrinos, They can be whatever. They can be spread out whenever they want. I don't have to. Again, the concept of world is not a physical. It's not people who say there are some proposals, strange proposals, that consciousness or some big enough object cause collapse. Collapse is a physical process. When it's a physical process, I have to say that when it's 10 to the 21 particles, then there is a collapse. And when it's one particle less, there is no. For me, it's just kind of a concept which helps me to make correspondence. It's just like it's correspond to describing experience. When we describe objects, it's clearly it's a chair, but some would say, no, now it doesn't look like a chair. Maybe it's not a chair. Maybe it's just kind of device on 4 wheels, because it's a question of definition. So you can, up to you. And everything there will be somewhat different decomposition. You can say that microbes are not macroscopic enough. You allow them in superposition. Fine. Everything. It's like very similar to the standard when you read textbook and you say there is a measurement. And then von Neumann says there is no, you can put the boundary whenever you want. And people are happy with it. Although they shouldn't. If it's a real process, you have to tell where exactly it's happened. But if it's not a real process, just something which helps to describe, it shouldn't be a problem. So what I say, all macroscopic objects, and everyone could, yes?
When you started this lecture, you said that in your view, the broad hope was that we could find a physics which would describe our universe, and in particular our experience, right? And then you went on and you said the hope that you were sort of predicating your belief in the many worlds interpretation on was that we already had that. Like the physics that we have now can describe our world, right? And then from that perspective, it's natural to sort of say, I'm going to write down a wave function for the universe, and this is like what the universe is. It's encapsulated in my wave function, right? Cool. And then so from that we move forward, and we say, what does that tell us? Well, certainly collapse can't be physical. Yada yada yada. We move on. We get to the many worlds interpretation, and now you've gone and you've introduced some very flaky language. Now you're sort of saying a world is stars, cities, and elephants, whatever we like, right? But it's clearly, I am sort of giving you my experience. I tell you that's a chair, and from that you write down my contribution to your total wave function or whatever, right? But at that point, it stops seeming natural to me to take the wave function as your ontological element. Like now it's no longer clear to me why we would choose to say, oh yes, the wave function, we can like write down the wave function for the universe and go from that, as opposed to say what Chris Fuchs likes, which is just say, quantum theory is a way of sort of like an extension of classical logic theory, right? Like it seems like we've lost the objectivity in our physical theory, which to my mind was originally the justification for taking the wave function as the ontological element of the theory. Am I making myself clear, or?
I'm not sure. Chris, I don't think he even trying. He kind of believes that it's impossible. He believes that it's impossible to have some mathematical theory which explains everything. So he gives up. I say that psi does describe everything. I want to see if my experience does not contradict this. Because I don't have other theory. First, I want this hope. The only hope is psi. I don't have any other good theory. Chris Fuchs doesn't provide a theory. He says, oh, okay, we can use it. It's helpful. I don't say it's not helpful. But I want more. I want a theory which explains everything. My only candidate is psi. But I understand Chris and many others here, it's just no way. It's impossible. There are contradictions. It cannot be so because this, and this. And I want to say, no, it's consistent. Your experience is not contradictory with the assumption that everything is just a wave function.
Right, so in many worlds interpretation, just a way of saying we've developed quantum theory to sort of explain the observations we see as we, I don't know, perform Bell experiments or whatever, right? Like we have this theory to explain some experiments that we can do. And now we say, we impose your hope on it and say, we want this theory to describe the universe. So we write down a wave function for the universe, right? And now you're saying, we're going to eliminate hidden variable type arguments according by whatever Bell says. And then all that's left, if we impose this hope, is the wave function. Like, is that your view? That's the argument that you're trying
I wanted to say it in a different place, but in many of these talks, as I understand, the Bell story and whatever was a basic, and the probability was a basic. From my point of view, quantum mechanics has a very small part about probability. Quantum mechanics explain why this table is stable, why this color is as it is, the spectrum of all these lights. Quantum mechanics explains everything around. It's a theory which tells me all what I want to know about why the sky is blue, everything. It tells me everything. And so why, and then comes this Bell thing and whatever, and now we say, forget about it, it cannot be true. You have to look for something different. I say, no. If you look at it carefully, and if you're ready to pay the price for parallel worlds, then for parallel experiences, whatever, it's not worlds in the sense, no multiplication. There is only one physical universe. But there are more experiences. And people, I think, like before, people wanted to say that the Earth is the center of the world. And then it's not a good feeling that you are not the only you. There are many of you, and not the most important one. I think I believe that this kind of reason why people, there are kind of historical other things. I think De Witt was trying to say that the many worlds is we split and put the worlds as ontological, completely ruined the whole idea. So if you put them ontological to have this mixture, no advantage whatsoever. My advantage is that I have a theory which explains everything. And unless somebody will tell me, oh, you cannot because it's it cannot be true, I will stay here. So my task is to see if I can go with it.
Right, I think we sort of skipped a logical step there, right? I mean, if we start with quantum theory, then the question is, how much of it can we take to be real without contradicting our experience, right? And so in your view, you're saying we can take the wave function to be real without contradicting our experience as long as we impose many worlds, right? And somebody like Chris Hooks might say, if we want the most natural constraints, then we just don't take anything to be real, and we say it's something normative, right? But those are two polar extremes. I mean, there's certainly middle grounds about like things that we can take to be real and not real in quantum mechanics. And it's not.
I would say alternative. I want a theory which explains everything. I don't want a theory which helps me to calculate things. So psi, many words is fine. The variant of Bohm, which is another deterministic theory, explain everything. It's also fine. I'm looking for this kind of theory. Maybe it's my preference. This is my starting point. Some people don't have this starting point. As from the beginning I said, my task is to understand how things are. And I believe that it's possible, and I believe that what we have, that quantum mechanics, all what we study, all physicists, this is all physics which learned, 99% of papers in all this physical review, whatever. This is true. I can believe that there is nothing, you don't have to change anything. You have to admit this strange thing that there are parallel experiences. That this allows you to do this. Now, and you have to work hard for this. There is now this simple correspondence. The simple correspondence is very nice. I would like to have it. If somebody will give it without too much price, I will buy it. All attempts, I think the Bohm has very many problems. And other candidates are even worse.
The question is, yes, I agree completely, right? If somebody gives me this theory of everything which agrees with my experience, then if the price isn't too high, I'll buy it, right? And the price for your theory is I have to accept that the universe is constantly split, or not, sorry, the universe, that worlds are constantly splitting off, all sorts of things, right? And in Bohm, I just have to accept that the position of things is somehow right. But like, what makes your price less than Bohm's? If you're gonna sell me your theory, I'm looking.
I'm trying to now give a picture which seems to be satisfactory for me, and then it's your task to say what was not satisfactory is what I was saying. I still didn't finish the whole picture. Now, but what I want to say is the word need not be ontological, because many people say, oh, when I say word is a vague concept, they say, oh, yeah, your theory is vague. No, it should. It's just explaining. I have theory which is not vague at all. The psi evolve according to exact definite equation. I tell you exact ontology. No, everything is exact. It's just when I try to make correspondent to experience, I say, oh, there are all kinds of concepts. There are different ways to explain it, this or other. Yes?
Yes. If object 1 and object 2 come within causal contact of one another, can we write a new psi object 1 / object 2 and remove the necessity of having psi 1 of object 1 and or psi I of object 1 and psi I of object 2?
If they come
within causal contact of one another. Can we write that there, what was previously those two psi i's, I don't want to call them wave functions, into one new psi I of describing both object 1 and object 2?
If the object is a ket,
yeah,
and another object, let's say, is a Geiger counter, and they come in an interaction like in the Schrödinger-Ket experiment, and then because of this interaction, there are kind of two macroscopically different states of a ket. I can write a one-wave function for ket and a Geiger and put it together. But I would not like it. Ket is a macroscopic object. I want him in a well-defined state. And here, well-defined state is a localized wave packet. I want ket to be localized. And if I consider the whole evolution with a Geiger and just works using Schrödinger equation, it will be in this proposition, being here and there. Not good for me. For me, word, every macroscopic object is very well localized.
So, regardless of these macroscopic objects, even if, so for instance, my water bottle and my computer are in causal contact with one another, but you would have a psi I describing each of these objects individually in that, yes? So where do we draw the line then? What do we call a macroscopic object? How low do we go?
So the question was asked, it's vague, you can, there is reason. Humans are macroscopic object, clear. And cats and dogs are too. Now, microbes, until it was electron microscope, I think you didn't have to put microbes in a particular state. But when you can resolve that position, then it's better you'll put. Different experiences are different stories. If I'm moved by 10 to the minus 23 centimeter to the right, it's the same story. So this is what's called what's well localized. All these different branches should correspond to all experience, all word. It's kind of a causal story which we know. The word which we know is a causal story. If the word with the Soviet Union intact, it's a different word. It's clear. But the word in which some microbe moved 10 to the minus 5 centimeters, and it's up to you. You can say it's different, you can say it's not. You look on some kind of piece of dust here, if you really see it where it is, then you probably distinguish, oh, the dust to the left or dust to the right. But it's very vague. Something clear, pills, big objects, heavy objects, they have to be localized. They cannot be both here and here. But small things, if you don't touch them, yes.
Chaos is that the tiniest.
No chaos. There's no chaos. No chaos. Which chaos? Chaos is classical phenomenon. There's no chaos. Chaos is the semantical theory about classical mechanics. Classical mechanics is wrong. No chaos. Yes.
So, as a sort of a meta question to a lot of this, I'll point out that a lot of people follow experiments like Anton Zeilinger's experiments with a great deal of interest to try to get an idea of where this macroscopic line is drawn. And there's a lot of questions like that. So I want to ask a meta question about drawing these lines. You've implied in what you said that the criterion for an experience or a history is different after a very precise measuring device is invented and applied. So if that's true, is it that the physics was changed by the invention of the device, that how the universe works, or that the physics that we need to use in order to satisfactorily describe our experience has changed even though the underlying rules didn't?
Nothing happens to physics whatsoever. Physics is only about psi r of t. All the rest, it's our interpretation of how we want to describe this. How we connect this. The theory is psi wave function, nothing else. And the theory, the same theory. But how you describe it, of course it's different. If you have electron microscope, it's better. You'll start to describe positions of atoms as different stories. If you had 2,000 years ago, it was crazy to do so.
So in other words, the universe doesn't care whether we've invented those, but
Sure.
physicists might care because we need to use different models.
It's not models. It's just different. You just have to refine, make it more refined and refine. It's not anything conceptually different.
Excuse me.
Yes.
What's the role of Born rule here in this? Because
Born rule.
we cannot talk about
Anyway, I will discuss Born rule from the beginning. I was planning only for the second lecture. Maybe now it will be even not for the beginning of second lecture. Later. Yes.
occurs continuously, or is it continuously?
Wait, we split. Yes.
So here's a question. So the ipsi, the big ipsi of t, that is a superposition of all of these ipsi i's.
Yes.
That's ontological.
Yes.
These ipsi i's, are they also ontological? Do we know about these?
Now, physics, using the current physics and using what we have current observation, we have all kind of reasons how to decompose it. And this decomposition also may be more helpful or less helpful. The physics itself, the ontology, is this big psi, the sum. But this decomposition is very important to say that this program is successful. If I can make the decomposition, which each term which at least one of the terms correspond to what I see, then I'm happy. Then I succeed in my task.
I think that's the distinction that maybe bothering some people is that when you mention these ipsi i's, if you think of them as ontological, then it makes a little bit of unease when you try to describe your experience as part of these ipsi i's. But if you say that this ipsi I is my description and the whole ontological state is actually just the ipsi, then that would sort of...
Well, that is a part of the theory. I have to connect experience
Exactly.
mathematics.
I'm just
So,
trying
the
to...
psi I and experience, this is kind of different physics, not the cosmology physics. It's just physics of how eye work, how network, how neurons work, so whatever. This will tell me how to make connection between psi object, me, when I'm in different states of mind. This is very important, especially for Everett. So, for me, what I have to do, all this psi I, every things which correspond to a word, have to be a product state for each object. Each object has to be in a particular state, and which means localized wave packets. Because interactions are local. This is a very crucial thing. Interactions are local, and these things should be well localized. Now, this is a tale which will take some time. The question, I see, this is kind of official time. So the question, should I continue? Well, what is the official time of the end of the...
But I suppose if people don't mind, we can go 5 minutes over. No? Okay, so 5 to...
Okay, so let's consider this tale of a single world universe. You're probably familiar with this tale in which the king forbade spinning on distaff or spindle or the possession of one upon pain of death throughout the kingdom. But I'm talking about the other one. The king forbade performing quantum measurements or the possession of quantum devices upon pain of death throughout the kingdom. So don't send photons through a beam splitter to a single photon detector. Don't go to this site. This is forbidden by law. Don't play with Schrödinger cats and Geiger counters. Just avoid any quantum optic laboratory. They just have to be abolished, avoided. Just take them all out. Now it's kind of tough to do this because it's very spread out. I think if you go like 100 years ago, it wasn't so a big restriction. Today, it's probably pretty difficult. Don't, if you have a fluorescent light which is kind of doesn't work properly, you're in real trouble because it's flicking, it's quantum event. You have to avoid this, for sure. Better not to use fluorescent light at all. It's dangerous. So I assume that there is a kingdom in which we don't do quantum measurement. When we don't do quantum measurement, I'm not so sure that there are splitting of words. It's not clear. If you ask me to bet, clear there are things which probably, because I can see only few photons, and beam splitters I cannot avoid. Just any kind of piece of glass or anything is a beam splitter. But what is dangerous single photon sources, this maybe I can abolish. Although it's not clear. But I can imagine this. Now, another thing why I think it's not completely, it's science fiction. But I can talk about this. I know at least one professor of physics, Larry Shulman, who have a whole theory with this kind of conspiracy of nature. He believes that the nature, even when we do this quantum experiment, has a conspiracy. And for all kinds of thermodynamical initial conditions, statistical, macroscopically different superposition of macroscopic objects never happened. This is his theory. But now I just want to consider Gedanken world in which I avoid all these things. I don't do any quantum measurements. And let's, if you're skeptical and you think it's impossible, just be with me. Let's say, imagine this. Now, kind of in this universe, there is only one world. No splitting. In fact, all objects, there is a product state of all objects, because all objects in particular well-defined state. All cats are not, nobody play with them. Cats in a particular state. They're all well localized all the time. Again, don't do it for a very long time. There is a spreading. But for reasonable time, they can be well localized. Now, in zero approximation, which is really kind of not physical, all particles are product states. Then some people, many people thought many worlds cannot be a theory, a real theory. It's in configuration space, not a real space. This one is a real space. Every particle is a real space. There is a clearly real space. Now, if I want to be a little more realistic and kind of to believe that it's not complete science fiction, we don't have to put all particles in a localized wave packet. All neutrinos, I don't care about them. Photons, which I don't use my single photon detectors, they can be in superpositions. So I have these objects, which macroscopic objects, big objects, they have to be well localized. The rest, I don't care. Now, particles which make, I should say a little more. Because if I look on all this kit, it's made out of molecules, out of atom. Atom has this electron, nuclear. To say that electron is a product state with a nuclear, it's kind of not a good idea. So really what's important is that the molecules or nails, they're in a particular state. It's also important from a physical point of view. The interaction with other things are not through electron of an atom. The whole atom interacts. People when talk about atoms as bosons. Atoms are not bosons. They're made of fermions. But very well approximation for very many experiments. They talk about atoms. So the fact that there is an entanglement between a state of atoms inside, it's okay. So something of this kind is not complete science fiction. So maybe the world, if in this kingdom, if for some reason people don't want splitting and they will forbid splitting, they will not make splitting, so we will live in one particular world. So this naive, just everything is product, less naive, that we had a center of mass, big objects, molecules which interact. They are well defined, otherwise are entangled because atoms should be kind of quantum. Clearly, electrons are entangled there. Now, if we look in this universe on density as a function rho, psi star psi, of all kinds of particles, in a real space, we'll see a normal picture. This will show a cat. This picture will give us exact picture of a cat. It's trivial if we consider this naive picture. It's a little less trivial if we consider this one. But it's pretty clear that in this one-world universe, the wave function is okay. You know, in this picture, if every atom, it's kind of a, now I look with a very big microscope on the position of every atom. It's well localized. And it's work in particular place. Now, what I will say is the first thing. This many-world picture, which is one-world picture, is equivalent to a textbook collapse. Why? In this kingdom. Because textbook collapse happens when you do a quantum measurement. You don't do quantum measurement. No collapse. It's the same story, the same theory. If you look on GRW Pearl, and in fact yesterday I discussed this with Philip Pearl, and he agreed with me. The wave function, his collapsed wave function, will be the same wave function as my wave function. It's in this rest, if there are many particles outside which are not related, some of them will be collapsed. But the well localized, the spontaneous localization it's broad enough. If it's well localized from the beginning, it's remained in the same state. Nothing happened. It works only when we have these different macroscopic superpositions. If I forbid them, then for all my systems, this remains the same. Now, Bowman trajectories. We have particles in every kind of, wave packets. Now, since there is only one, they sit here. If there are superposition, some of them might be empty. Here, they're not empty. And this is very small. And the particle has to be inside. It cannot run out outside. So the picture of these particles, the picture of these small blobs, it's the same picture. In fact, since Bowman trajectories look like a classical trajectory, it's the whole story. If we want to make a correspondence with experience, the Laplacian determinism, Newtonian mechanics, this is the same situation. So I claim that at least in a single world universe, the many worlds give us a good story. And it is, some people, it's not clear. Some people tell me that it's not. And please tell me why you think it's not. Some people say in principle it's a configuration space, so it cannot be a real description. I say the density of all particles in a real space, and it's the same description all over. In contrast, all this quantum mechanics as probability theory, this is particular possibility for the board. Special kingdom, special case. But this is completely irrelevant for them. No probability whatsoever. No Born rule, no anything. And so they cannot help us. This gives me the whole picture, the whole reality. This cannot be a basis because it doesn't help anything. So I think. What? One of the things I'm not allowed to have Geiger counters. If some
Also, it's okay as long as you don't count it. Okay.
if they're not macroscopic, there are all kind of particles, microparticles going around. I don't care. No different stories. So I think this is clearly, yes.
Okay, and then we'll meet Thursday then to continue.
We'll meet Thursday to continue. You are welcome to ask questions here in the room, or please. I would like would like everybody, if you can, to send your objections for what you don't like, at least until this moment about many work interpretation.
So do people have any questions? Any further questions more than the ones that we had already? If not, then let's thank Dr. Brady.